Now I'm going to propose a question that no one has the answer to. It deals with objects called graceful trees, or to be more precise, graceful labelings of trees. Take a tree and label its vertices with the numbers 0, 1, 2, up to the number of edges. We now know that we can do that because the number of numbers here is the number of edges plus 1, which equals the number of vertices. Now take those numbers and subtract them, and use the number that you get, or the absolute value of that number, as a label for the edge between the respective vertices. We're going to get a certain number of positive numbers, and all those numbers will be between 1 and the number of edges. If we in fact get all the numbers between 1 up to the number of edges, then we say we have a graceful labeling. For example, I get to choose how to label the vertices, or you do, but I can't hear you. There are 2 edges, so I'll use the numbers from 0 to 2. And now I label the edges with the absolute value of the differences between these numbers. And lo and behold, I do get all the numbers from 1 up to the number of edges. This won't always happen. You have to choose your labeling carefully. What if, for example, I have 1, 2, 3, 4 edges, and I use the numbers 0 through 4? Or how about if I just label 0, 1, 2, 3, 4? Now when I take differences, I get here 1, here 2, here 3, here 2. I don't get a label 4, and that's because the label 2 has appeared twice. But if I'm more careful, and I choose this labeling of vertices, then I get these differences. And now I do get all the numbers from 1 to 4. Here's a graceful labeling, here's a graceful labeling. This is a disgraceful labeling. It's not known if every tree has a graceful labeling. Here's a problem that 4 computer scientists in Montreal worked on, 3 of them at McGill University and 1 at Concordia University. Their paper, appearing online on May 1st, 2012 in the Journal of Graph Theory, is called Transversals in Trees. Suppose you have a binary tree, and each node is a valve that water can pass through. Which valves can you close to prevent water from reaching any of the leaves? For example, if all the valves are open, and you were to pour water into the top node, then it would flow all the way down, and all of it would come out through the leaves. If you were to close this valve and this valve, you would no longer get any water coming out of these 2 leaves, even though their valves are open, because they're blocked at this valve. And you would not get any water coming out of this leaf because its valve is blocked. But you would still get water coming out of this leaf because there's a channel of open valves leading from where the spout of where the water is pouring in to here. If now you were to close these 4 valves, now water cannot pass out of any of the leaves. The water pouring down this path gets blocked at this valve. The water pouring down this path gets blocked at these 2 valves. And because the water cannot pass out of any of the leaves, we call this collection of 4 closed valves a cut set. This collection of closed valves is not a cut set because it allows water to come through. And here, the empty set of closed valves is not a cut set because, again, water can get through. Brooks is the leader, in fact, the financier, and passes his evil plans to his immediate subordinates, Jane Doe and Bungie. They, in turn, pass these plans to their subordinates. If the leaves are the foot soldiers who will carry out an attack, say, then you don't want any one of them to get the plans. So law enforcement wants to arrest a cut set of the people. Even though Gold Teeth is not the real name of the individual represented by that node, or so I assume, this is not abstract theory. This is a real network. At least it's the picture provided by a policeman. Kevin Blake, who is a policeman with Jamaica's Ministry of National Security, and who is the head of the National Intelligence Bureau in that country, has actually used these ideas to break up at least one criminal gang. And this is a picture coming from his work. Kevin Blake also uses computing in order to improve law enforcement on the island of Jamaica. The computer scientists in Montreal that I mentioned before found the binary tree that has the fewest cut sets among all binary trees. In fact, we could talk about ternary trees, or trees where no node has more than b children for some fixed number b. In the case of binary trees, that b is 2. And the 4 computer scientists in Montreal found the tree structure that has the fewest cut sets amongst all trees with the property that no node has more than b children. It's clear that these trees fall into some sort of pattern. And rather than having to draw the trees, I just want to be able to describe which member of the family I'm talking about with a number, the depth. I'm just inventing this quantity, but it's pretty clear what it should mean. This one node tree has depth 0, this tree has depth 1, this tree depth 2, this tree depth 3, and this tree depth 4. You get the idea. So now if I look at trees of increasing depth, the number of vertices we already know will be 1, 3, 7, 15, 31, 63, 127. We can see the pattern. And the number of one-element cut sets is just 1, 1, 1, 1, 1, 1, 1. You also see the pattern. This is because the only way to prevent water from flowing out of any of the leaves by removing a single node, just one, is by removing the top node, the leader of the gang, as it were. If you remove anyone else, for example, in this case, if you would remove this node, then water could still pass down through this channel. Here, if you were to remove, say, this node, water could still pass down through several different channels. The only way to keep water from flowing out of any of the leaves is by removing the leader. But now, how many two-element cut sets are there? In the case of the tree of depth 0, there are no two-element cut sets because there are no two-element subsets. Here's the tree. There aren't 2 elements to remove. In the case of this 3-element tree, there are 3 two-element cut sets. We can remove the leader and then anyone else, and those are cut sets because we've removed the leader, and the leader by himself was a cut set. Or we could remove both of the leaves, that is, close the valves, and that would be a cut set. Water can't come out of any of the leaves if both leaves have closed valves. So that would be one cut set, this would be another cut set, and this would be a third cut set. And that contributes to that 3. In this tree, it turns out there will be 7 cut sets with 2 elements. Let's see what they are. I could remove the leader plus any of the other 6 elements. Once I've removed the leader, there's no way water can pass through. Or I could remove these 2 nodes. And once I've done that, there's no way water can pass through. If I don't remove the leader, and I don't remove both of these guys, then there will always be some channel that water can pass through. For example, if I remove those 2, it's clearly not a cut set because water can pass through here, out of that leaf. And now we have a quiz. How many 2-element cut sets are in this tree of depth 3? And now we have the answer. The answer is 15. As before, we could take the leader, and that's a cut set by himself, but we want a 2-element cut set, so we could take anyone else, and there are 14 other people. Or, again, we could take these 2 guys at depth 1. If we do anything else, there will be a way for water to pass down out of one of the leaves. This brings us to quiz E. What about the depth 4 tree? How many 2-element cut sets are there? Or the depth 5 tree, or the depth 6 tree? And it's clear how the pattern works. So the answer is 31, 63, 127. Now let's look at these trees and consider the number of 3-element cut sets. As before, with the depth 0 tree, this has 1 node. There are no 3-element cut sets because you can't remove 3 elements. There is only 1 element. And similarly, with the depth 1 tree, there are 3 elements to remove. So if you're going to remove 3 elements, there's only one way to do it: remove everyone. In the case of the depth 2 tree, how many 3-element cut sets are there in the depth 2 tree? That's quiz 3. And the answer is 21. You could remove the leader, and that by itself is a cut set. And so you could remove any 2 of the other 6 people. And how many ways are there of doing that? I could take these two. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And if I don't take the leader, I could take these two and any of the other four. Remember, I'm not taking the leader. This is clearly a cut set. Water cannot pass these 2 points. And then I could take these 3 or these 3. But it turns out any other collection of 3 people that I remove will allow water to pass through. For example, if I take these 3, water can clearly pass down through there. So the answer is 21 3-element cut sets in this tree of depth 2. And you know where this is going. Quiz Pi, in the tree of depth 3, how many 3-element cut sets are there? The answer is 105. Again, you could remove the leader plus any 2 of the rest, and there are 14 others, and that's 14 choose 2, or 91. And then we could remove these 2, and then any one of the remaining 12. This is because we've already considered all the cases where we choose the leader, so that's 12. Or we could remove these 3 or these 3, and that gives us a grand total of 105.